Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. A breakthrough in computational mathematics or in the supercomputer solution of a grand challenge problem is particularly worthy of being a benchmark in the history of the computer. That breakthrough is noteworthy if it changed the way we looked at the computer and the internet. With the supercomputer that communicates across processors and do so synchronously, and computes within processors and do so simultaneously, we now have answers to previously unanswerable grand challenge questions. I'm Philip Emeagwali. Calculus and algebra are the languages that I use to describe grand challenge problems arising in science and technology. Mathematics is as old as civilization. Mathematical knowledge is abstract and immutable. Where did human knowledge of mathematics come from? New mathematics came from the minds of research mathematicians working at the farthest frontiers of mathematical knowledge. New mathematics came from equations that were unseen before. New mathematics occurs when we understand how to solve the toughest problems arising in mathematics and how to solve a problem that could not be solved before. The new computing paradigm, for which I was known but not known well, was an automatically programmed and email communicated messages that I sent to and received from equidistant processors that were across the surface of a globe. In my new supercomputing paradigm that represents a new way of counting, the toughest problems arising in science and engineering and mathematics could be chopped up into 1 billion smaller problems that could be solved in a one problem to one processor corresponded manner and solved 1 billion times faster than was previously possible. My new paradigm in supercomputing was the diametrical opposite of what I learned as a 19-year-old when I began programming supercomputers back on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. In that old paradigm of large-scale computational mathematics, I programmed one isolated processor to take what seemed to be forever to solve one grand challenge problem of mathematics and physics. My contributions to mathematical physics and computational mathematics came from the bowels of my new internet that was a new global network of 65,536 processors that became a virtual supercomputer. I was asked, who invented mathematics? Mathematics is a living body of human knowledge whose pieces were invented by research mathematicians whose names were quite often lost in the midst of time. The contributions of Philip Emeagwali to mathematics is this. I contributed 9 partial differential equations to the branch of mathematics called calculus. My contributions to mathematical knowledge also includes these equations. I contributed 9 partial difference equations to the branch of mathematics called extreme scale algebra. My contributions to mathematics include this. I invented how to solve those finite difference algebraic equations and how to solve them by parallel supercomputing them across an ensemble of millions of processors. My contribution to mathematics also include this. The mathematical knowledge of how to solve the grand challenge problems arising in science and technology. Back in the 1980s, the US government publicized a list of 20 grand challenge problems of computational mathematics. Those interdisciplinary problems were at the crossroad where mathematics, science, and computer science met. Those mathematical problems were called grand challenges because no mathematician could solve any of them. I was the first computational mathematician to discover how to solve the grand challenge problems and to discover how to solve them across my new internet. That is a new global network of 64 binary thousand processors. That is a virtual supercomputer. What new mathematical knowledge did Philip Emeagwali contribute to mathematics? My contribution to extreme scale computational mathematics is abstract and cannot be understood by a high school math teacher. The reason is that new mathematical knowledge are discovered at the frontiers of knowledge, and to reach that frontier in turn requires 3 decades of training in the mathematical sciences. It took me 30 years from learning the times table to learning the partial differential equations of mathematical physics to arrive at the frontier of massively parallel supercomputer knowledge, where new partial differential equations of calculus and new partial difference equations of algebra can be discovered. The greatest mathematicians are famous for their contributions that increased our body of mathematical knowledge. The contribution of Philip Emeagwali to mathematics is this. I discovered how to solve the toughest problems arising in computational mathematics. Back in 1989, I was in the news headlines because I discovered how to solve such grand challenge problems and solve them across a new internet, that is a new global network of 65,536 processors that were identical to each other and that shared nothing between each other. Each processor was akin to a tiny computer that operated its own operating system. My contributions to mathematics was the cover story of the May 1990 issue of Siam News. The Siam News is written by research mathematicians and written for research mathematicians. Siam is the acronym for the Society for Industrial and Applied Mathematics. Siam is a 14,000-member society of applied and computational mathematicians. My image and representations of my contributions to mathematics have been reprinted in high school mathematics textbooks and in school reports on inventors. Back on July 8, 1991, in the nation's capital, Washington, District of Columbia, I delivered an invited lecture on my contributions to mathematics. I delivered that lecture at the largest international congress of mathematicians called ICM 91. That congress is the Olympics of the world of mathematics and is held once every 4 years. The research lecture that I delivered on my new discovery of how to message pass initial boundary value problems, and that I delivered at that mathematics congress, was over the heads of the attendees. That research lecture was on my new parallel processed way of solving a system of partial differential equations and solving them across a new internet, that is a new global network of processors. As an aside, the partial differential equations on my green board photo that was dated May 9, 1996, and that was widely reprinted as a sidebar in high school mathematics textbooks and in school reports, were formulated for multi-dimensional and multi-phase flows of crude oil, natural gas, and injected water that were flowing 1 mile deep below the surface of the earth and flowing across a production oil field that is the size of a town. The stability analysis of the numerical discretizations of those systems of partial differential equations is a grand challenge of algebra, because the direct stability analysis on the nonlinear system of partial difference equations with variable coefficients was impossible. I did what any research computational mathematician must do, namely, I investigated the theorized stability condition of a simplified version of the original initial boundary value problem. In the early 1980s, and as a research mathematician in College Park, Maryland, United States, I conducted extensive experimental stability investigations on the actual initial boundary value problem that must be parallel processed and solved to pinpoint with greater accuracy the deposits of crude oil and natural gas. From the perspective of the mathematician, climate modeling is an initial boundary value problem of calculus that must be discretized and reduced to a large-scale problem in algebra that is the discrete counterpart that is defined at finite points in space and time, and that approximated the original mathematical problem that was defined at infinite points and therefore will take forever to solve exactly. Back in the 1980s, the extreme scale computational mathematician did not know how to parallel process the extreme scale climate model and did not know how to chop that grand challenge problem into a million smaller problems, and did not know how to parallel process that ensemble of problems and do so with a one-to-one problem to processor correspondence, and do so across an ensemble of a million processors that were tightly coupled to each other. The contributions of Philip Emeagwali to mathematics is this: I discovered how to parallel process that grand challenge problem and do so across a new internet that was a new global network of 65,536 processors that were tightly coupled to each other and that shared nothing between each other. I was asked, why should the African student study mathematics? Mathematics is more than memorizing the times table of arithmetic. Mathematics is more than learning how to solve the quadratic equation of algebra. The African student must study mathematics because it's a subject that nurtures critical thinking. Critical thinking, in turn, is the most undervalued experience in education. This lack of critical thinking skill explains why a 13-year-old northern Nigerian that did not learn geometry proofs is easily convinced by Boko Haram jihadists to strap herself with a suicide bomb. To dig deeper into the quadratic equation of algebra and to be reflective of how the partial differential equation of calculus enables Nigeria to discover and recover otherwise unforeseeable crude oil and natural gas demands a significant time for reflection and thought. My passion for performing the fastest calculations began in early 1964. I was then a 9-year-old in Abo, Midwest region, Nigeria. Each late afternoon, I practiced solving 60 to 100 arithmetical problems and solving them within 60 minutes. I was practicing for the all-important 1965 Common Entrance Examination into King's College, Lagos, Nigeria. At that time, King's College was the most elite secondary school in Nigeria. The entrance examination into Nigerian secondary schools was akin to American Scholastic Aptitude Test that was at the level of a 12-year-old. That entrance examination consisted of two parts: a set of 60 questions on the English language and another set of 60 problems on arithmetic. Each problem must be solved within 60 minutes. For the 20th month onward of January 1964, and in the late afternoons, and in the evening, and in the living room of our 3-bedroom house, my father drilled me with 60 increasingly challenging arithmetic problems. I used a stop clock that stops at the 60th minute. With daily practice for the forthcoming entrance examination, the questions on mathematics became easier than those on the English language. At the All Nigeria Federal Entrance Examination, I selected the faraway all-boys boarding school, King's College, Lagos, as my first choice. I was confident that I scored 100% in the mathematics portion of that entrance examination. Because I had been rehearsing for that entrance examination and practicing it almost daily for nearly 2 years, I was able to finish the 60-minute test in 10 minutes. At the practice sessions, I only scored above about 90% in the English language portion of that entrance examination. So my total score of 190 was not high enough to get me an admission into the very competitive King's College, Lagos, Nigeria. My failure in 1965 to get into the most sought-after secondary school in Nigeria was a big blow to my father's ego and to mine. At age 10, my confidence in my mathematical ability was supreme. That confidence stayed with me, and I was not afraid to tackle previously unsolved mathematical problems, such as solving initial boundary value problems of mathematical physics and solving them for the first time and across a new internet that is a new global network of processors, each akin to a tiny computer, that were identical to each other and that shared nothing between each other and that were tightly coupled to each other. I was confident because I was identified as very talented in mathematics and as someone that will shine in the field of mathematics. Back in early 1965, at age 10, at St. John's Primary School, Boji, Abo, Midwest Region, Nigeria, my school headmaster, Mr. Okwechime, would not have been surprised if he was told that a quarter of a century later that I will be the cover story of the top mathematics publication, namely the May 1990 issue of the Siam News that is published as the news journal of the Society for Industrial and Applied Mathematics.
Insightful and brilliant lecture.